This is going to be an introduction to vectors in three-dimensional space. To put it briefly, basically everything that went on in 2 dimensions goes on in 3 dimensions as well. There will be one minor point of interpretation, but we'll see that when we get there. In three-dimensional space, if I have a point P, I drop down into the xy plane and identify its x and y coordinates. The amount that it is above or maybe below the xy plane is the z coordinate. So instead of associating pairs of numbers with points, I'll have triples of numbers instead. Likewise, for another point Q, given 2 points in three-dimensional space, draw the arrow from one point to the other, and we're going to call that, in this case, the vector from P to Q, just as we've done before. This vector, this arrow, in three-dimensional space is going to have a direction and is going to have a length. The length of the vector is the distance from point P to point Q, which we know how to calculate if we have the coordinates of P and Q. As we did in 2 dimensions, though, if I just tell you the linear direction, the straight line direction, along which a vector points, and I tell you its length, there are lots of vectors like that. Here's a picture of a bunch of arrows. If I didn't know any better, I would think that I were in the xy plane, and these are just equivalent vectors drawn in the way that we did in 2 dimensions. There's more to it than that, though. I actually drew these arrows using some software called GNU Plot. If there's any interest, we can talk about that another time. But one thing that you can do with GNU Plot is you can take a picture that's been drawn in three-dimensional space and rotate it. These arrows are in three-dimensional space, they're parallel to each other, and they all have the same length. Visually, to see that they're parallel is easy enough. I'll just turn it. It's easier to turn with the keyboard here. I'll turn these, and you'll notice all of the arrows appear to be getting very short, even though they're not. Their lengths are still the same. They appear to be dots now. That's because the arrow, if this were truly three-dimensional, is sticking up out of the plane of the screen and pointing straight at your eye. If I use my cursor keys, I can turn this sideways, and I see that no such thing is going on. I can turn it in this direction as well. Despite appearances, these vectors are not in a common plane. But even so, they all have the same direction, and they all have the same magnitude. So just like in 2 dimensions, we'll call these kind of vectors equivalent vectors. In every vector, I start at the initial point, I end at the terminal point. I'll call the amount that the x-coordinate increases delta x, the amount y increases by delta y, and z by delta z. Out of all vectors that have the same length and direction, one of them has its initial point at the origin. The terminal point will be the amount that x, y, and z increased. I can write vector u in this case, which is equivalent to vector p to q, as end minus starting x coordinate, end minus starting y coordinate, end minus starting z coordinate. This is exactly the same thing that went on in 2 dimensions. To be a little bit more concrete about it, suppose the point P has coordinates 1, 2, and 3, while point Q has coordinates 3, 6, and 11. Following my end minus start recipe, I'll take the coordinates of the end point Q, 3, 6, and 11. I'll subtract away the coordinates of the initial point, 1, 2, and 3, and I'll find out that the component form of the vector from P to Q is 2, 4, 8. The magnitude of the vector from P to Q is, on one hand, the distance from P to Q, or, on the other hand, the distance from the origin to the point where x is 2, y is 4, and z is 8. If I think about that second idea, and I use the Pythagorean theorem, I'll be calculating 2 minus 0, quantity squared, 4 minus 0, quantity squared, 8 minus 0, quantity squared, add them up, do the square root. The result is I take the components of the vector, square them, add them up, and do the square root, just as you did in two-dimensional space. The length of the vector, the arrow that starts at the origin and goes to 2, 4, 8, is radical 84. We could simplify that in a variety of ways, but I'm just going to leave it that way for now. In 2 dimensions, we reasoned out that if I have a number times a vector, the most natural way to write that down is to take the components of the u vector, multiply them by the number c, and then that will be what we should call c times u. The exact same reasoning will convince us that that's what we should do in 3 dimensions as well. If I want to add vectors together, as in 2 dimensions, I add corresponding components. Likewise, if I want to subtract 2 vectors, I'll subtract them 1 component at a time. At this stage of the game, we don't know how to calculate very much with these 3-dimensional vectors, but one thing we can do is this. If I tell you the coordinates of points P, R, and Q, I can determine whether or not they lie on a straight line. If I want to think of traveling from P to Q, there's going to be a vector that represents that. The length of the vector tells me how far I have to go, and the relationships between the different components tell me the direction, as we'll see later. Suppose that P, R, and Q are on a straight line. Starting at P and traveling towards Q, I eventually hit R, and then continuing without changing my direction, I eventually reach Q. If that's the case, then the vector from P to Q, the vector from P to R, the vector from R to P, the vector from R to Q, or even the vector from Q to R, all lie along parallel straight lines. All of these vectors would be multiples of each other. P to R, for instance, might be a third of P to Q. R to Q might be 2/3 of P to Q. R to P might be negative 1/2 P to Q, and Q to R might be negative 1/2 times P to Q. I can determine this by looking at whether or not one of the vectors involved is a multiple of the other one. Now, on the other hand, suppose that R is not on the straight line from P to Q. So in this case, I form the straight line segment from P to Q, but R is not there. That means that if I travel from P to R, I have to change direction in order to travel from R to Q. Those two vectors are not along the same straight line direction. They are not parallel. They're not multiples of each other. So given this situation, I'll just form two of these vectors involved and see if one of them is a multiple of the other one. And whether it's a positive multiple or a negative multiple is irrelevant to me. As an example of this, I'll take the point P to have coordinates 1, 2, 1, Q, negative 6, 5, 1, and R, 1, 7, negative 2, and I'd like to determine whether or not these 3 points are on a straight line in three-dimensional space or not. Calculation of vector P to R gives 0, 5, negative 3 for the components. The vector from R to Q is negative 7, negative 2, 3. Neither one of these vectors is the 0 vector. One of them has a component equal to 0. The other one doesn't. There's no way these vectors can be multiples of each other. Therefore, these 3 points don't lie on a straight line. This has been a quick introduction to vectors in three-dimensional space. In the next video, we'll look at a couple of applications. Then we'll talk about the dot product of two vectors, and then we'll be able to do more things than we can do right now. In the meantime, I hope everyone has a good day. I'll talk to you again soon.